Bismillahirrahmanirrahim. Assalamu alaikum. Moving forward, ladies and gentlemen, so we will discuss in this session, uh, like it is going to be a step towards explaining our understanding Cauchy-Goursat theorem. But in this session, at first, we will look at some of the terminologies that are required to explain this Cauchy-Goursat theorem. So, in simple words, I would say that what we are going to see in this, theorem or in this discussion is we will consider a function f of z and a domain. Let's say this is a domain D. Moreover, this f of z is analytic and D, right? Analytic and D, analytic function. So, what is an analytic function? We will define. So we will assume we have a function which is analytic on a particular kind of domain. So when it comes to domain, so we will discuss now shortly the simply connected domain and multiply connected domain. So like we will be talking about these two specific kind of domains. Moreover, if we have an analytic function and we have a particular kind of domain in such a way that we consider a closed and simple contour inside this domain, and we will, this is a C which is positively oriented simple closed contour lying inside a particular kind of domain, and our task is going to be to see this f of z dz, the integral or the contour integral over this simple closed curve, and it will turn out that this remains the same, or whatever it is we will be looking into it. So we will see in short, we will be considering a function which is analytic in a specific domain, and then we will see its contour integral within that domain. So before we get into the statement of the theorem, I would love to define some of the terminologies, and the first natural terminology that we need to define is going to be the analyticity of a function. So let's see what do we mean by an analytic function. Let's define analytic function. Analytic function at a point z. Consider a complex valued function, a complex valued function w to be f of z over a domain, let's say D, right? So we have a function defined over complex valued function defined over a domain D. So we say f of z is analytic at a point, say z naught in the D, if what happens, if number one, f of z is differentiable at z naught. So function has to be differentiable at z naught. Additionally, we can find a neighborhood or an interval, a neighborhood u of z naught such that f of z is differentiable at every point of u. So let's simplify the definition in our own words. So what we are saying basically is following. So we have a function f of z and we have a domain. Let me say this is a domain, and we take a point z naught. So we will say that this f of z is going to be analytic at this point z naught, Number one thing that f of z naught should make sense. In other words, the derivative of f at z naught should make sense. Additionally, we should be lucky enough to find a neighborhood over this z naught. Let me say this neighborhood is basically an open ball over this point u, such that this f prime at z also possible, or we can find the derivative for every z and u. So like it is differentiable at every z inside the u. Simply connected and multiply connected domains. Simply connected and multiply connected domains. Multiply connected domain. So on one side we will define simply connected domain. On the other side we will define multiply connected domain. So let's define. We say that a domain means a set. Domain D is said to be simply connected if every simple closed contour C lying within D can be shrunk to a point without leaving D. So we are saying that uh, a domain is said to be simply connected if we have got so let's say this is a domain, and we will call this domain as simply connected. So I should make it over here. So like this is a domain. I will call this domain, let's say this, in the rectangular form, or however you like to make it. So I have a domain. I will call this as simply connected if I take any closed simple contour. If I take any closed and simple contour, and I wish to shrink it to a point, I don't need to leave this. So I can shrink every simple closed contour to a point without leaving this domain. So if this is the case, then my domain is simply connected. You can also see this example where domain D is containing a curve, simple closed contour. As far as definition of multiply connected domain is concerned, we can define any domain which is not simply connected is basically multiply connected. But we can relate the simply connected domain with the multiply connected domain in a way that if we have a domain and we are lucky enough that every curve can be shrunk to a point without leaving that domain, then that domain is simply connected. But if on the other end you have a domain, and you wish to you have a domain, and you are you can find a curve that can be shrunk, but for that shrinking you need to leave this domain. Here I can't visualize this, but I can give one perfect example where you can see that how this will create a problem when we shrink a closed simple contour inside the domain. How will we have to leave the domain? So we can see here you go. You can see that we have got this domain over here, and is this domain simply connected? No, because we can find a contour. This is the contour. We can find a contour such that if I want to shrink this contour, I will have to leave this domain. So there is a hole, in other words. on the same lines I can find a contour over here which is simple and closed, and if I wish to shrink this I will have to leave this domain. For shrinking to a point I will need to leave this domain. In other words, I can say that if a domain has holes, then it is a multiply connected, and if a domain does not have any hole, then it is simply connected. One more thing I need to mention, that when I was saying that this should be positively oriented, that means it should be counterclockwise oriented, right? So like when I was defining, in the start, I was saying that I need to have an analytic function. I need to have, simply connected and multiply connected, either of these domains, and I have a contour which is positively oriented. So you can make sense of it. Positively oriented means counterclockwise. So one more thing now, I would say, uh, if so, I can say that simply connected domains do not have don't have holes, right? But multiply connected domains can have holes, right? One other example that I will discuss now is going to be, uh, you know, I want to see that if I have this domain where 1 is less than equal to the modulus of z less than equal to 2, I wish to see this set whether this is, simply connected or multiply connected. So we are basically saying here that 1 is greater than square root of x square plus y square less than 2. Or I can say that 1 is less than x square plus y square square root, and this is square root of x square plus y square is less than 2. We can plot this on the plotter Desmos. So here is the plot, right? So we can see this plot and we can discuss whether this is simply connected or multiply connected, right? So there is one clear hole you can see. So this is going to be multiply connected. But one other thing that we can see is how can we relate this with the definition that we have already seen of shrinking a contour. We can say that a curve is going to be multiply connected if we can find a contour, and when we shrink it, we have to leave the domain. So I can find this contour now. You can see that this contour is entirely lying within this domain. So the contour should be lying within this domain. But when I will shrink this, this will be, I can shrink this to a point, and the point is going to be the origin. So when I will shrink this, I will, I can, but I can compress it to origin. But for doing so, I will have to leave this domain. And when we leave the domain, for shrinking a contour which is simple and close inside a domain, and we have to leave the domain, then we say that this domain is not simply connected, but it is multiply connected. So it is multiply connected and it has one hole. Okay. One more thing is, if a curve has one hole, then we call it doubly connected, and if it has two holes, then we call it triply connected. So previously, this domain, this one over here, was triply connected because there are two holes. So in this way, you can define some other terminologies as well, right? This was all about, terminologies. Next, we will be moving towards Cauchy theorem.